Hey, hello there. Let's talk about today's Leetcoding challenge question, word search. Given a two-dimensional board of characters and also a search word, we want to determine whether we can construct the word by sequentially connecting adjacent letters on the board. The adjacent here means horizontal or vertical neighboring, so it's a four directional moves. Note that the letters cannot be used more than once. So once we choose to use certain letters to form the prior part of the word, in the subsequent choices, we couldn't use it again. So that's pretty much the question. Let's look at this example. We have a board with 3 rows and 4 columns. Now we are trying to construct the word A, B, C, C, D, E. Obviously, we want to start this construction from the positions on the board that starts with the first letter A, so because the word starts with A. So once we match that, we try to find the next character. We're looking around the neighbor of A and find B. So now we match the 2 characters. The third thing, the next step is trying to match the next character in the word. So it's a C. So we see that we're now gradually building out this candidate paths in the word on the board. So once we match A, B, C, we try to do that even further. We moved on to get another C for this example. And eventually we will basically match everything. So the path in the end has the same length of the word. So that's the time when the candidate path be promoted to the solution. As long as we find one solution, we can return true. In the other case, let's see that we are trying to construct the word ABCB. The partial path candidate path is this highlighted here, ABC. In the next step, we're trying to grab B around the neighbor of this highlighted C here. We find there's no neighbor that's a character B, so this candidate has been pretty much destroyed. So we go back to AB and try to find C in other directions. Since that there are no other C's, we'll go back to A. At that time, we will try to find B in the other direction, but it's a S down there, so it's not possible. So we declare that starting from this A, there's no way that we can find a solution to this problem. So we will start with other positions and pretty much repeat this process. So in short, it's backtracking or DFS. So to handle the case that the letters may not be used more than once, there are a couple of ways. One thing is to, as we are growing this candidate path, candidate crossing of the characters in the board, we can use some extra data structure to memorize the word we have used, the character we have used. Or we can just simply replace the cell on the board by some non-character stuff like empty space, so that in a subsequent search we would never really use it. So that's also possible as well. Yeah, so let's code this thing. Before we code, because it's backtracking, it's pretty much try all the possibilities. The time complexity is the number of cells on the board. That's all the possible starting positions for this kind of candidate building backtracking process. And so that's m multiplied by something. The backtracking would take 4 to the L time, because at any given particular cell, in the maximum you're looking at the 4 directions. And if the length of the word is L, you're going to repeat this for 4 to the power of L times. So that's the time complexity. And for space complexity, it's basically the length of the word. So yeah, let's just start code this. First thing, we grab the size of the board, because we're gonna do the looping with this in mind. And the next thing we do is to basically lay out the main part for this function. We're going to examine the board cell by cell. If we have the matching in the first position, then we start the backtracking. Or we can, in the backtracking logic, to deal with that. If the character doesn't match, we terminate early. So it's easier to, it looks easier. Obviously, in the main part, we're trying to look at the first character in the word. So that's the main part for the code. Then what we need to do is to lay out the detail of this backtracking process. It takes three things: the current position on the board, and the ice character that we want to match from the word. So if I is equal to length of the word, that's the case when we successfully matched the whole word. Then we just return true. Otherwise, we want to determine, so this means finished. We want to test whether the character at this given position on the board is equal to the character that we want to we need. So the condition is that it's a valid position on the board, and also it has a value that's what we need. If that's the case, we want to look around the four neighbors and kick off this backtracking process from that position, trying to find the next word. But before we do that, we want to mask this current character so that we don't revisit it. But we have to restore it in the post order. So once we determine that there's no way we can match the whole thing in some later stage, we want to go back and restore this character on the board. So we have to first remember it. So here I'm just replacing it with empty space. I'm looking at the four neighbors now. And kick off this backtracking again from the neighbor's position with this aiming at finding the next character. If we can successfully doing this over and over and reach the end, when the i's position, when the I becomes equal to n, that indicating we match the whole word, we're going to return true. Otherwise, we pretty much do nothing, return a false. We can ignore it as well. So in Python, if nothing happened, it would just be none. So this should do. Oh, it's called board, it's not green. Sorry. I have to restore the character in the backtracking order. Yeah, so that's it. That's the backtracking solution to this problem. Basically, usually when I analyze backtracking, I think of the candidate that's growing. And inside the backtracking logic here, we are making a choice here. That's basically this four directional moves. And once we make a choice, the next position we go, we are growing the candidate by extending that by one more position. In this case, it's not a physical candidate I'm carrying in the backtrack. It's rather the empty space on the board. The empty space on the board is marking the candidate sequence of characters that I'm using to find the word. So so I have to go back and restore that after I made the choice and determine that the choice is invalid. So that's why I'm restoring it here. I guess the distinction between backtracking and simple DFS is that once you make a choice and you determine that choice is fruitless, there's no meaning, then you have to restore the modification you did. So that's an extra step on top of DFS that makes backtracking slightly different from DFS. Yeah, so the time complexity is all the possible starting locations indicated by the nested double loop here. And the 4 to the L is indicated by this for loop here. We try 4 positions, and every position we just recursively call this backtrack. So it's 4 to the length of the word. For space complexity, it's the call stack of this backtrack. This can go as long as the I become equal to the length of the word. So that's the levels of recursive call it's going to happen. So that's the space requirement. Because I'm modifying the board to indicate the current path is not using any extra data structure. Yeah, so that's this DFS backtracking solution to word search. If you're interested, I have a video about word search too, which is nothing but search for multiple words with this backtrack procedure. So instead of just using the index and find the i's position of the word, it's trying to match the try path. So the stuff you put on the backtrack core is a node object in the try and the current position. So slightly more complicated, but the main part is pretty similar. You have the nested loop here, and you have the backtrack, which is nothing but can we promote this candidate to the final solution? If so, we add it. Otherwise, we're going to verify the current matching and mask the board position and go make a choice of the 4 directional movements. So in terms of the main logic in the code, it's pretty much identical to this one, except that it's using a try data structure to do the matching. But with that, you can match a set of different words on the board. So if you're interested, you can check out the video over there. I'll try to put a link up there. So that's the code. That's the question for today.